welcome to this lecture series on noise control in mechanical systems with me Professor Sneha Singh from IIT Roorkee, and so far we have been discussing about the module on sound signal analysis, and in the sound signal analysis module we have covered about the time domain analysis and then the spectrum analysis or the frequency domain analysis. So, today we will continue our discussion on the spectrum analysis, and in particular we will see two important spectrum ways of representing the sound waves, and we will see first of all the common spectral distributions in the mechanical systems and the two important frequency spectrum that are used throughout the world, which is the octave and the 1/3 octave bands, and how do you combine the sound pressure levels in these bands. So, these are some of the topics to be discussed in this lecture. So, what are some of the common spectral distributions in the mechanical systems? Some of the two most common type of spectra is a white noise and a pink noise. These are the two idealized spectra. So, what is a white noise? When a random noise is there which has equal energy per hertz, and thus it has got a common spectral density level all throughout its frequency. That is called as a white noise. So, here what happens is that the energy content is the same for all the frequency bands, or it is having a flat response throughout all the frequency bands. So, obviously the spectrum of the white noise is going to look like this. So, any random sound, okay, an ideal random noise which is a combination of various sources of various frequencies and intensities. So, an idealized random noise can be written as a white noise because it is unbiased and has uniform distribution throughout the frequency. The other kind of common spectrum is the pink noise. And here what happens, that the power spectral density is not constant per hertz, but rather the power spectral density or the amount of acoustic power which is present per frequency interval is actually inversely proportional to the frequency of the signal. So, in the previous class we have seen that the spectral density distribution with respect to frequency. So, the small, or I can say the small del I for every frequency is inversely proportional to that particular frequency over which that sound wave exists. So, pink noise is one of the most common signal that is available for biological systems. So, most of the biological systems, they emit pink noise type of spectra. So, you can see the power spectral distribution of this pink noise, where the intensity is uniformly decreasing with respect to the frequency. It is a linearly, you can say overall the envelope is almost like a line that is decreasing with frequency. A linear decay is happening here, whereas over here it is almost a flat response or constant distribution. So, spectrum analysis, quickly a recap is that the spectrum analysis or the frequency analysis is the process of converting any time varying signal into its frequency components, and the methods used are Fourier analysis and its variants, and it is very useful for noise control applications because our human hearing is highly sensitive to the frequency of the sound that is being heard, and hence just the time signal, the time variation of the sound is of not that much importance. It is of importance, but it does not give the complete picture. In order to understand how this sound will affect the human beings and the living beings, the frequency component of that sound needs to be analyzed, and hence the spectrum analysis becomes important. And some of the common types of sound spectrum, they are linear spectrum, where the intensity of the sound is being represented in a linear scale of the frequency. So, which means that every new frequency band is after a constant difference from the previous band. For example, you can either have from 0, 10, 20, 30, 40, this is a linear scale of the frequency, or you can have, and the narrow band is when this del f becomes 1 Hz, then we call it as narrow band. This is one type of the linear spectrum where you analyze for 0, 1 Hz, 2 Hz, 3 Hz, 4 Hz, 5 Hz and so on. For every particular Hertz, what is the frequency content? So, both of them here, in both these cases the frequency is in a linear scale, okay, it is linearly varying, and the interval of the scale is fixed or constant, okay. Here for example, the del f is 10 Hertz, this is the interval of every scale or the band, and here the del f is 1 Hertz. However, sometimes given the the nature of the human hearing, how sensitive we are to some lower frequencies, whereas our sensitivity to some of the higher frequencies is still low. So, given that sometimes it is more useful to represent the spectrum of a sound using a logarithmic kind of a frequency band. So, in that case, two types of frequency bands are mostly used, which is the octave spectrum and the 1/3 octave spectrum. So, in the octave spectrum, what happens is that every next frequency band is just the double of the first one, okay. So, if FL is the lower limit of one band and FU is the upper limit, then the upper limit of the band is twice of the lower limit, and the central frequency is the geometric mean of this upper and lower frequency limit, okay. In the same way, for the 1/3 octave spectrum, in every band the upper limit of the band is 2 to the power 1/3 times the lower limit of the band, and the central frequency once again is the geometric mean of FU and FL. So, these are some of the equations which are the generic equations followed by every frequency band within the octave and the 1/3 octave spectrum. So, let us see why we use this spectrum. So, we use it because in order to facilitate the comparison between the measurements from the different instruments and the manufacturers across the globe. So, in order to standardize the measurements and analysis of sound signals, the ISO has prescribed to use these standard bands. Okay. So, usually the octave band where the every new limit of the frequency or the upper limit is twice the lower limit, it is a more wider band, as you can see, and the 1/3 octave band where the upper limit of frequency in every band is 2 to the power 1/3 times the lower limit. This is a more narrower band. So, the octave band here is the wide bands which are used for some quick frequency analysis, and 1/3 octave bands are typically these narrow bands which are used for more detailed frequency analysis of a noise source. For example, you can see these two spectra here. So, as you can see, these two spectra are for the same noise source, okay. For the same noise source, the octave band for example is giving you that, okay, the peak is occurring at okay, so sorry, this is not for the same noise source, but for two different noise sources, just two different octave and 1/3 octave bands are given to you. So, here suppose you want to do a quick analysis and quickly see what is the frequency content like. So, you would come to know that the frequency is typically peaking around this zone, and in the rest it is decaying sharply. Suppose you want to go for more further detailed analysis, then here it shows a typical 1/3 octave band of a different noise source, and what you can see here is that, okay, over the detail you can see that, okay, there is a frequency peak here, and then there is a small decay, then another frequency peak, then over here there is a frequency peak and then a decay, and these are some of the shorter frequency peaks. So, you can do a more finer you can see the frequency content with a finer frequency resolution. You can see further peaks and more detailed spectrum you can see using the 1/3 octave band. So, let us see for an octave band the generic relation between any band. So, let us say this is your octave band. Let us say your first band is like this, and then you have the second band, the third band, and so on. These are the various bands, and this is your the FU1, let us say, and this is so this is FL1, this is FU1 for the first band. So, the lower frequency limit and the upper frequency limit for the first band in octave. and then accordingly this is your the lower frequency band and the upper frequency limit. So, the lower frequency limit and the upper frequency limit in the second band, okay, FL1, FU1 and FL2, FU2. Okay, and the generic relation for every such band is that the upper limit of that band would be twice of the lower limit and the central frequency would be the geometric mean of the two. So, let us see what is the relationship between the successive central frequencies. So, what we observe here is that, let us say the central frequency of some, let us do for the two successive bands 1 and 2 and see what happens. So, the central frequency of, let us say, the first band would be root over of the upper limit frequency multiplied by the lower limit frequency, and the upper limit frequency would be twice of the lower limit frequency. So, this we expand further. So, it becomes twice of FL1 into FL1. So, it is overall root 2 times of FL1. So, in the same way, the central frequency for the second band once again is under root of FU2, FL2, and by the similar derivation it would be root 2 times of F of L2. And as you can see here that the bands are successive in nature, there is no gap in between these bands. Okay. So, bands are usually continuous in nature. So, the F of L2 is same as the F of U1. So, whatever is the upper limit of the first band, your second successive band starts from that frequency onwards. So, that upper limit of the previous band is now the lower limit of the next band. So, FL2 is equal to FU1. So, this FL2 is FU1 and which is root 2 times of twice of FL1. So, what you see here is that it is actually 2 times the central frequency of the first band, because this was the central frequency of the first band. So, twice of this. So, the central frequency also follows the same relation, which is the central frequency of any successive band would be twice of the central frequency of the first band. So, that would be the relation between the central frequencies, and the bandwidth for each band would be the upper limit minus the lower limit frequency. Okay. In the same way, let us see the relationship between the 1/3 octave band. So, here Fu, the upper limit of any band is 2 to the power 1 by 3 times the lower limit of the band, and the central frequency is once again the geometric mean of FU/FL. And in the same way, suppose this was your first band, FL1, and FU1 of this band is there, and there is something called FC1, and then this another successive band which is F, whose lower limit is FL2 and FU2 and so on. So, using the same analysis, let us say the central frequency for this very first band would be under root of F of U1 into F of L1, and F of U1 would be 2 to the power 1 by 3 times of FL1. Okay. In the same way, if you do it for the second one, what you get is, once again it could be represented using the same relations, which is but FL2 is the same as the F of U1. So, where the first band is ending, that frequency is the starting point for the second band. They are continuous in nature. So, hence when you replace this, FL2 is simply F of U1. So, which means if you solve it further, F of U1 is 2 to the power 1 by 3. So, 2 to the power 1 by 3 times of root over this quantity, and this quantity is nothing but your central frequency for the first band. So what it means is that just like the relation between the upper and the lower frequency, the central frequencies of the successive bands also follow the same relation. So the central frequency of any ith band would be 2 to the power 1 by 3 times the central frequency of the I minus 1th band. And just like here in this case, this was twice of FC1. Okay? And the bandwidth once again is the difference between the upper and the lower frequency. So this shows the octave bands obtained, the lower frequency is shown, the upper frequency is shown. So for example, this is your band, it starts from 31.5, ends at 44.5, and its central frequency is around, it starts from 22. So it starts from 22, ends at 44.5, and the central frequency is around this. The second band starts, it's continuous in nature, starts from 44.5 here and goes till 63, 89, and it has a central frequency around 63 Hertz, and so on the bands continue. So this shows the typical, the low frequency, upper frequency and the central frequency of these octave bands. So what it also means is that suppose, a graph is given of octave band, let us say this typical graph, and a certain intensity has been reported for some band. Let us say we are trying to see in this graph, the peak is being reported around 2 kilohertz. Okay. So if you go back to this, so if suppose you are getting the highest peak in the 2 kilohertz of central frequency band, which means that in the frequencies around this to this, we are getting the peak, okay, because so we are representing the entire band 1414 to 2828 Hertz by the single central frequency, and this is the octave band central frequency for the 1/3. So these are the octave band central frequencies and 1/3 octave band central frequencies. So in the 1/3 octave band, one octave is divided into 3 parts. So there are 3 individual central frequencies and the 3 individual bands which together comprise a single octave band, and so on. So these are some of the tables that are already available in the internet as well in various other books. It is something which you can always keep in mind and memorize, so that the octave, interpreting any octave band or 1/3 octave band becomes easy. So let us say, for example, let us say in this graph over here, we are getting a peak around this point, which corresponds to a 1/3 octave band of, it's between 250 and 400, it would be a 315 Hertz peak. So what it actually means is that over here, so in the frequencies between the range of 283 to 353, we are getting a frequency peak, okay, and so on. These are the various values. So let us say now that suppose there are 2 sounds which are coming together and they are present in the same space, okay. So suppose we have 2 different sound sources and they are together active, and both of them have got some individual waves, and together when they are active, what would be the corresponding wave? So suppose when the 2 sounds, they are 2 sound sources, when they are playing together, they are said to be coherent. So the sources could be coherent or incoherent. So coherent sources are those which have the same frequency, they have the same waveform, and they also have a constant phase difference. Okay, so same frequency, same waveform and a constant phase difference. These 3 conditions need to be satisfied. And any 2 sound which is not coherent, which is not satisfying each of these 3 conditions, which is the same frequency, the same waveform, and the third condition is a constant phase difference throughout time, then the 2 sounds will become incoherent in nature. So let us see that if suppose there are more than 1 sound sources present, how do we combine their sound pressures together, given that they are either coherent or incoherent. So whenever incoherent sounds, they are present together, then the total intensity due to these sounds is actually a vector summation. So the total intensity is a vector summation of their individual intensities. So the intensities, they add over. Whereas when the coherent sounds, they are present together simultaneously, then the total acoustic pressure is actually, a vector summation of the individual acoustic pressures. So that is the difference. So let us derive the combined sound pressure levels for, in the case when we have more than one sound sources present in a medium and we want to find out the combined sound pressure level, given that the individual sound pressure levels are given to us. So let us say we have got various incoherent sources, P1 to n number of incoherent sources, and they are present together or simultaneously in a medium, then the total intensity would be a summation, vector summation of the individual intensities. So which means that, and we know that the intensity is directly proportional to p square by rho c, and this rho c, because all of them they are present together in a medium, so this rho c is constant for all these sounds. We want to see what would be the combined level at a point. So P rho c is going to be constant. So which means that the intensity would be directly proportional to P square. So P effective whole square would be P1 square, the vector summation of P1 square, P2 square, P3 square, Pn square. So here I have added plus and minus both signs. Suppose the sources are present together and you want to find out the combined sound level, you would use plus. But suppose if some source was already present and it has been now put off, so its sound pressure needs to be subtracted from the rest, then you will be using the minus sign accordingly, according to the case. So when all the sources are present, it would be plus. When some sources was present initially, now it is absent and its effect needs to be removed, you will use a minus sign. So suppose this is the general summation of the intensities of the various sources. If you divide the left hand side and the right hand side by the P reference whole square and then do a 10 log 10 to both the sides, you would end up with this equation. Now by definition, this is what? This is the sound pressure level, this is the total sound pressure level due to the n sources. Okay. This is the total sound pressure level due to the n sources, and this is 10 log 10 of this big quantity here. So let us see what are these quantities in terms of the sound pressure level of the individual sources. So if you take any Pi by P reference whole square, so the level of ith source is 10 log 10 of Pi square by P reference square. So Li by 10 becomes log 10 of this quantity, and then 10 to the power Li by 10 becomes Pi square by P reference square. And we know that the total SPL due to the n incoherent sources, L effective is 10 log 10 of this big quantity, and each of this individual quantity here is what? It is simply 10 to the power Li by 10. So P1 square by P reference square simply becomes 10 to the power the SPL of the first source divided by 10, and so on. So ultimately you end up with this equation. So what it means is that the total SPL, let us say, due to the presence of n number of sources is 10 log 10. So it is logarithmically added up. So you do the 10 log 10 off, and within the brackets you have 10 to the power the SPL of the first source individually divided by 10 plus minus 10 to the power the SPL of the second source divided by 10, and so on till 10 to the power the SPL of the nth source divided by 10. So this is how you can combine the individual SPLs to get the overall SPL, where SPL is obviously the sound pressure level. Okay, so in the same way, suppose coherent sounds are present. So in the case of coherent sounds, it is the acoustic pressure that gets added vectorially. Okay, so you do the vector addition of the acoustic pressures. So here, suppose you have an acoustic pressure P1 and another acoustic pressure P2, and the phase difference between them is phi, then the net F pressure would be the vector summation of P1 and P2 with the angle between them as del phi, which is the phase difference. So this is the formula P1 square plus P2 square plus minus 2p1 p2 cos del phi. So, plus is when sources are added to get the total source, and minus is used when sources are subtracted. So, one source is getting absent, like that. So, again if you divide it by P reference and then do a 10 log 10, you end up with the L effective, where this is the total SPL of the n, the 2, here we have only derived for 2. So, this is the total SPL of the 2 coherent sources, the total SPL due to the 2 coherent sources, which is given by this big expression here. Now, we already know that this is what? This is simply 10 to the power L1 by 10, and we have already derived that this is what? 10 to the power L2 by 10. We have already derived this. Let us see what these are in terms of the individual SPLs. So, this is your L1, this is your L2. So, L1 by 10 is log 10 of P1 square by P reference square. So, this is this thing, and 20 log 10, suppose you want to find out what is this quantity. So, if you do 20 log 10 of this entire thing, then it would be same as 20 log 10 of P1 by P reference plus 20 log 10 of P2 by P reference by the property of logarithm. So, ultimately this expression is what? It is the summation of the individual sound pressure levels of the two sources. So, now you remove the 20. So, basically what you do is you divide this expression by 20 throughout. So, you will get log 10 of this quantity is L1 plus L2 by 20. So, ultimately this quantity would be what? It would be 10 to the power L1 plus L2 by 20. So, with this derivation, we get this value is 10 to the power L1 plus L2 by 20, and this is our total sound pressure that we had represented. So, we can say that this would become 10 to the power L1 by 10, this would be 10 to the power L2 by 10, and this would be twice of this whole thing, which is 10 to the power L1 plus L2 by 20 into cos del phi. So, this is a slightly more complicated expression for the total SPL due to presence of two coherent sources, okay, plus sign for presence, and suppose subtraction you have to do, then you will use minus sign, okay. So, this is a more complicated expression if you compare it with the addition of incoherent sources. Let us say here this was our expression, 10 log, suppose there were only 2 incoherent sources present, then what would be our expression? It would be 10 log 10, and within the brackets we have this 10 to the power L1 by 10 plus 10 to the power L2 by 10, okay, if suppose it was incoherent sources. So, the same thing for incoherent sources, would be 10 log 10 of this thing value plus 10 to the power L2 by 10, and it would end here. But if the sources are coherent, then in that case you have this quantity, and inside that you have some additional quantity. So, which means that when the sources are coherent together, their combination gives a higher sound pressure level compared to when the sources they are incoherent in nature. I would like to close this lecture. Thank you for listening.